Swayam Prabha. Digital India. Educated India.
Okay, so let me have your attention, and please take a notebook or piece of paper and please make notes. So you see, we were discussing rather the case of plane curves, okay, and in the case of plane curves, what we looked at is this idea of what is called a sine curvature, okay, and you see, originally the sine curvature was designed only to adjust with the sine normal, so that you can write the equation in the correct way, so that the acceleration vector always pointed towards the center of curvature, okay. But then it's geometric adjustment, but it also has a mathematical or analytic meaning, namely that the sine curvature is actually the rate of change of a turning angle, okay, and we proved for any continuously differentiable unit vector such a turning angle exists, okay. What is the advantage of this analytic interpretation of this sine curvature? The advantage is that you are able to derive the so-called Frenet-Serret differential equations, okay, which give a set of differential equations, two first order differential equations, which you can think of also as a single matrix differential equation, okay, and it's a first order differential equation, and the solution of that equation is nothing but your curve, okay. So it is the equation of motion of a particle tracing the curve, all right. And of course, it is a unit speed curve, so you must think of a particle traveling at unit speed along that curve, okay. And the equations of motion are given by the Frenet-Serret differential equations, okay. And what is the Frenet-Serret differential equation? Basically, it relates the derivatives of the Frenet-Serret frame with the frame itself, okay. What are the Frenet-Serret frame members? They are the unit tangent and the unit sine normal, and the sine normal is defined by taking the unit tangent and rotating it anti-clockwise or counterclockwise by 90 degrees, okay. Now we also use this to say that because this matrix controls the curve, okay, namely this matrix gives the differential equations whose solution is the curve, okay. This is one way of saying that the curve is controlled by its sine curvature. Yeah, if you want a more perfect statement or a more accurate statement, the statement will be that you should allow the curve to be moved by a rigid motion, okay, which is a composition in general of a translation and a rotation. And what happens is, under rigid motion, you see the sine curvature will not change, okay. And important thing is, the rigid motions will maintain the orientation, so the sign of the curvature will not change, okay. So for example, the sine curvature changes sign if you take a positively oriented circle and a negatively oriented circle, okay, though the circles may be of the same radius, okay. So the big deal is that somehow the correct statement is that you have to take equivalence classes of plane curves, and the equivalence relation is two curves are equivalent if one can be moved to the other by a rigid motion, okay. Then this set of equivalence classes of plane curves, you have to assume them to be unit speed and parameterize on a fixed interval, okay. That is in bijection with all possible curvature functions, okay. That is the statement, okay. This is the mathematical way of saying that the curvature, the sine curvature completely determines the curve, and we will see this more generally for three-dimensional space curves. So I am not proving this now, okay. But I want to say that this sine curvature is the most important thing there, and its analytic interpretation as rate of change of the turning angle of the unit tangent That is what is most important. Okay, so what we want, and we also saw another thing, namely if you took of course if you take a curve which is part of a straight line, or you take a curve which is part of a circle, then the curvature is constant. In the case of a straight line, it's going to be 0. In the case of a circle, it's going to be constant. It's equal to the reciprocal of the radius. Okay, and the sign is given as positive if you are traversing the circle in the anti-clockwise sense, and you have to give a negative sign if the the circle is being traversed in the clockwise sense. Okay, and you can also try to prove the converse of this, namely if you have a curve, plane curve for which the sign curvature is 0, then it has to be a straight line, and if the sign curvature is a positive and non-zero, of course, then it has to be part of a circle. Okay, so and this is easy to prove using the idea of turning angle. Okay, so this turning angle thing is very, very important. Now what we have to do is that we want to do the same kind of things for space curves. Okay, so you are now looking at a space curve, a curve which is in 3 space. Okay, and then you want to again have the same kind of theory. All right, and so if you take a space curve, what happens is that you will now have a parameterization which is given in terms of 3 coordinates. So if you take a space curve, you have to think of it as there is an open interval AB on the real line. Okay, and there is a parameter t here, and you have this mapping gamma equal to gamma of t. Okay, so it sends t to gamma t. Now the point is that this gamma t is now moving, it's a moving point in space. Okay, so you have you have the xyz coordinates here, and then you are having a curve like this. Okay. So this is your gamma of t. Okay, and if you take any point there, then it will be given by it's a point in 3 space, so it's given by 3 coordinates, the x, y, and z, and they will depend on t. So basically you will get 3 functions. Okay, so you will get x of t, y of t, and you will get t. Okay, this is how the coordinates will look like, and that will be your gamma t, gamma of t. As t varies, the point on the curve varies, so the x coordinate, the y coordinate, and the z coordinate also depend on t, and they vary. All right, and of course standard example of a space curve is that of a helix. Okay, and we have so that is a simple example to think of. All right, now we want to study space curves, and you want to do 2 things. First thing is you want to understand the curvature of space curves. Okay, and then you would like to have you would like to have a Frenet-Serret set of formulas, or you would like to have this Frenet-Serret differential equation. Now what happens is that you see there is a new character that has to be introduced, which is the torsion. You see, in the case of a plane curve, the moving frame consists of only 2 vectors. Because you are on the plane, you need only 2 vectors to express any 2 linearly independent vectors to express any vector, and we take them to be orthogonal to each other and also unit length. Okay, just like I cap and j cap are the usual unit vectors you take along positive x axis and positive y axis. Okay, but now the point is that this you see, this frame is moving along the curve. So what happens is that on the curve you need 3 if you want to think of this in 3 dimensions, you actually need a triad. You need 3 vectors. Okay, so you need 3 orthonormal vectors. All right, and whenever you have 3 vectors, there's also this issue of whether you're going to choose a right-handed set of vectors or a left-handed set of vectors. So we will take a right-handed set of vectors. Okay, and then once you have these 3 vectors, you can have the analog of Frenet-Serret differential equations in in the 3-dimensional case. In the 2-dimensional case, what was the Frenet-Serret differential equation or the Frenet-Serret relations? You took the unit tangent and you took the signed unit normal, and you wrote their derivatives in terms of these 2. Okay, because the derivatives are also going to be vectors in the plane. and they can also be resolved in terms of these two. Any vector on a plane can be resolved in terms of two linearly independent vectors. Of course, they are orthonormal, they are orthogonal, so they are linearly independent. Okay. So see, the point is that if you want to do this in 3D, what you need is first 3 vectors. All right. Now the question is that how are you going to make sense of these 3 vectors? But the starting point is always only one vector you always have for a parameterization, which is a tangent vector. Okay. You have to make sense of 2 more vectors. So how are you going to do it? Now curvature always gives a vector which is pointing towards the center of curvature. Okay. So in this case, there is already something interesting that's going on that I told you long back during the introduction. That you see, if you take a plane curve, what happens is that there is a best fitting circle at every point of the curve, which is the circle of curvature, or it's called the oscillating circle, and it has a center of curvature. So there is a center of curvature, and then once you know the center of curvature and the point, you have the radius of curvature, and its reciprocal is the scalar curvature, which is just the magnitude of the sine curvature. All right. But you see, when a curve is moving in space, you take any point, you have a tangent. Okay. A priori, there are an infinitude of planes for which pass through that tangent line. So you see, the picture is like this. My curve is passing like this. Suppose this is my curve in space, and I take some point here. Then I have this tangent vector. Okay. So I have this so-called so again, let me say the following thing. To begin with, whenever we so this is something that you should always keep in mind. Whenever you go to Frenet-Serret, or whenever you try to write Frenet-Serret, remember that everything is done only for unit speed curves. Okay. So it's a very, very important thing that you should remember, that this whole Frenet-Serret setup works only in the unit speed case. That's because you see, you are saying you're taking the signed unit, you're taking the unit tangent, and you're taking the unit normal. Okay. And you want the acceleration to be in the direction of the unit normal. Okay. Up to a sign. But you see, acceleration is derivative of the tangent vector. Okay. And you want the derivative of the tangent vector to be perpendicular to the tangent vector. That will not happen unless the tangent vector has constant length. Okay. So in general, if you draw a curve, okay, and which is not parameterized by unit length, you see the tangent vector. If you take the tangent vector and you take its derivative, the derivative need not be perpendicular to the tangent vector. Okay. So you must always be careful that whenever you are looking at a Frenet-Serret kind of situation, where you want to apply the Frenet-Serret, you should have only unit speed parameterizations. Okay. So this is something that you should keep at the back of your mind. So so let me say the following thing. For the moment, let me just not worry about parameterization at all. Suppose this is just gamma of t itself. Okay. What happens in the case of a space curve? So you have this tangent. So this is gamma dot t. That is all right. That is a tangent vector. Okay. And this is at suppose this is the point gamma t. Let me write it like this. Let me erase this. Okay. Now through this point, there are many tangent planes. Okay. After all, through a line if you give me a line in space, there are an infinitude of tangent planes that contain that line. So you will have so if I draw, let me try to draw a picture. Let me see. So I can have a plane like this, and then I can have another plane. I can have one more. Let us say like this. Okay, and I can have one more. That can be many. All right. I can have also, so let me put something here, green. So I can even have a plane like this if you want. Okay. So you see, I can have many planes, containing that line which contains the tangent direction, all right. And therefore, what should be the circle of curvature? See, it should be a best fitting circle for the curve at that point, and because it is a circle, it has to lie on a plane. It has to lie on a plane. That plane should be a plane which contains the tangent to the curve. That's because the circle of curvature should have the same tangent as the tangent to the curve. So basically what you want is that among these infinitude of planes that contain the tangent direction, there should be exactly one which should contain the circle of curvature, okay. And again, the beauty is that there is one. There is a unique such plane, and that plane is called the osculating plane. There is a particular plane called the osculating plane, okay. Among these infinitude of planes which contain the tangent line, there is only one. That's called the osculating plane, and that contains the circle of curvature. So what is happening in the space curve case is that even before you determine the circle of curvature, you need to determine one plane among the infinitude of planes that contain the tangent line, okay. And the point is, again, geometry does it, okay. And you can also justify it by calculus, that there is a osculating plane and it contains the oscillating circle, and you have the center of the circle is the center of curvature. Now once so this whole thing can be approached both geometrically, it can also be approached analytically, okay. And you can use see, in the case of plane curves, we used plane geometry. If you are now going to do it in the space of in the case of space curves, you have to use space geometry or 3D geometry, and again you have to use calculus, and you can make sense of all this. I will not go into this. What I want to say is that at this moment, I want you to understand that it is because of geometry which can be justified completely by analytic methods, that there is a special plane at every point of the curve which contains the tangent to the curve, called the osculating plane, and that contains that special circle which is the osculating circle, okay. So this is the first fact. So let me draw one more picture. So you see, you have situation like this. So I have this curve now. I take, so this is my curve, and of course I always need to put an orientation, okay. So I have this point which is given by gamma t. The tangent vector is given by gamma dot t, okay. And this gamma t, there is a well determined plane called the osculating plane, and this osculating plane contains the circle of curvature and the center of curvature. So you see, we have this osculating plane, okay. So you take it for granted that there is an osculating plane. This plane contains the the tangent vector at the point, okay. And what is happening is, this curve is briefly at that point, the curve is briefly entering the plane and then leaving it. You should think of it like that. The curve is briefly entering the plane at that point, and then it's instantaneously leaving the plane, so that at that point the tangent lies on the plane. You see, that's how you have to think about it, all right. And on this plane you have this there is a circle which is the circle of curvature. So you have, on this osculating plane, you have the circle of curvature, okay. And of course this is also called as osculating circle. Okay, and there is also a point which is the center of the circle, which is the center of curvature. Okay. Now you see, you have, so once this is there, I have the geometric acceleration vector which has to point from the point on the curve towards the center of curvature. So I have this vector now, okay. And you see, therefore what I want to tell you is that you see, if you start with a parameterized curve, what is originally given to you is only a tangent direction at every point, that is just by taking derivative. But geometry gives you an accelerating geometric normal direction, okay. And once you have two directions, it's easy to get the third direction by deeming the third direction to be in such a way that these three form a right-handed system, okay. So that is how you get these three mutually orthogonal right-handed system of vectors, which are called the Frenet-Serret frame for the space curve. So it is actually three vectors now, okay, and as the curve moves, these three vectors are moving, okay. So now you can imagine that, you see, if I take this picture, there is going to be this is going to be 90 degrees, okay. And so mind you, let me be very careful, this arrow that I have drawn pointing to the center of curvature is not gamma double dot. Let me say, it is not gamma double dot, it is a geometric acceleration vector, okay, and that's because it will be gamma double dot only if gamma dot was a unit vector or gamma dot is constant, okay. Therefore the problem is that, in general, if you take a curve which is not unit speed, you take gamma double dot, it will not be perpendicular to gamma dot, okay. But what I am drawing here is a geometric acceleration vector, which is by definition geometrically from the point on the curve pointing towards the center of curvature, okay. So this will give you the correct direction as gamma double dot only if gamma was unit speed, okay, which will be the normal direction, right. And then the third direction is determined by, so you have this is the so-called normal, okay, and then you have a third direction which is going to be given by, so let me use a different color. So you see, maybe even for the normal, let me use a different color. So there are three vectors, so I want to just show them separately. So there is so here is one, so this is the normal direction, so this is the second one. Now the tangent and and mind you, this is geometric normal, and it's not gamma double dot, okay. Then the third one is determined by taking the condition that gamma dot geometric normal, and the third one, they should be right-handed system. So what you have is, you have one more, and so there is a name for it, it is called the binormal, okay. So you have the tangent, then you have the geometric normal, and then you have the binormal, which is perpendicular to both of these, so that these three form a right-handed system. So there is one more here like this, there is one more guy here like this, and this is called the binormal, okay. And the point is that this is 90 degrees, mind you, this is 90 degrees. So you see, it's a three-dimensional diagram, you should imagine this, okay. So this is how you get it geometrically. That's so the idea is that, therefore, at every point on the curve you are getting a frame. So you see, therefore what happens is that you are getting three mutually perpendicular vectors, and of course you could take three unit vectors along those three directions, and these three directions are said to be the frame directions for the Frenet-Serret frame for a space curve, okay. So let me repeat, if you take a space curve, what is initially given is only the tangent direction. Then because of geometry, you get an oscillating plane containing the tangent direction and an oscillating circle, which is a circle of curvature, and a center of curvature. Therefore you get the direction from the curve to the center of curvature, which is a geometric normal, and this is of course perpendicular to the original tangent direction. Now the third direction is given by taking something that's perpendicular to both of this, and that's called the binormal, and so that these tangent, normal and binormal form a right-handed triad, okay. So that's how you get the three directions. And what you must understand is, as the curve moves, the tangent, the normal and the binormal, they are also continuously moving, okay. And as the curve moves, what is happening is that, you see, at every point even the oscillating plane is changing, okay. And as the oscillating plane changes, the circle of curvature on the oscillating plane is also changing. So you see, it's a very dynamic kind of situation, all right. So now the question is that, always, whenever you have something geometric, then you have to worry about writing it analytically. Okay, so how do we do this analytically? So let me. So the idea is that if you want to do things analytically, you start using some standardization. Namely, you take a unit speed curve. The advantage of the unit speed curve is the tangent is unit speed. Therefore, the acceleration is always automatically perpendicular to the tangent. Okay, the derivative of a unit vector is perpendicular to the unit vector. All right, we have already seen that. So you get the normal direction, but then how do you write the normal direction? How do you define the normal direction? Because I always told you that there is always an issue trying to define the normal direction. There is only a normal line, and which of the two will you choose? You see, this is the issue for the case of plane curves, that we had to fix a normal direction as the signed normal. Okay, we said take the tangent and then rotate it 90 degrees counterclockwise and call that the sign normal. Okay, but here which one are you going to take? So the beauty is that you are led by the Frenet-Serret equation that you got in the curve case. See, in the curve case, so let me write this. In the plane curve case, what do we have? See, in the case of a plane curve, you see you have, so this is on the plane, so I will draw it like this. So you have the curve gamma, let us say, and so we are of course I am going to write Frenet-Serret, so I better use capital gamma of S. Okay, then at every point I have the gamma dot, that is the tangent vector. Okay, and I'll just call it as t cap of S. Okay, then there is the sign normal, which is like this. This is ns of S cap. This is a sign normal, and you go 90 degrees in the anticlockwise direction. And what happens is that we have written the Frenet-Serret. What is the Frenet-Serret? It records the derivatives of these two with respect to these two. Okay, so you have t cap dot ns cap dot is given by this beautiful skew symmetric matrix, which involves the sign curvature, and here you will have t cap, n cap, ns cap. Okay, so this is what so this is what you get. Okay, and if you write out what is the normal direction, you see, so t cap dot, if you write it out as two equations, you will get t cap dot is equal to ks ns hat. Okay, and you will get ns hat dot is equal to minus ks t hat. Okay, these are the two equations. Okay, and this is these two are equivalent. One is a matrix form, the other is writing it as two separate equations. Now, how is the normal? See, look at this equation. The normal direction is 1 by ks t cap dot. So this is what it is. Okay, and this makes sense if the curvature is not safe. Because I have to write 1 by ks. So now what you do is that you mimic this. If you take a space curve, okay, take it to be unit speed parameterized, then you have the unit tangent vector. All right, what you do is that you define the normal direction. Okay, and now it is no longer signed normal. Okay, you just call it the normal, and when you take curvature, there is no idea of signed curvature. You have to take only the absolute curvature, and you use this to define what is called as a normal. It's called the principal normal. The principal normal for a space curve will be the acceleration, okay, divided by the magnitude of the absolute curvature. That's how you define it, and the definition comes from the intuition is from the plane case. Okay, and what you have to remember is that there is no signed curvature in the space case. Okay, and there is no signed normal. Okay, so you will be worried that once signed curvature and signed normal are not there, it might cause some trouble. Because you see, if in the plane case, if sine curvature and sine normal is not there, then there is a problem. If you don't consider sine curvature, you cannot distinguish between a positively oriented circle and a negatively oriented circle of the same radius. It's the sign that keeps the track of the orientation. But the problem with rigid motions is that rigid motions preserve orientation. Okay, the only thing that will change orientation is reflection. Okay, so this seems to be somewhat of an issue. Okay, but actually there is this issue is resolved in the following way. What is going to happen is we are going to define one more curvature called the torsion. Okay, and the torsion that you are going to define will have a sign. Okay, and what will happen is the sign of the torsion will determine the left-handedness or the right-handedness. Okay, and that will keep sense of everything. Okay, see, when you have a right-handed system in 3 space, okay, give me any plane and give me any normal, I have a sense, I have an anticlockwise sense recorded on every plane if you give me a normal direction. Okay, so the right-handedness of the system takes care of everything, and that is controlled by the sign of the torsion which is going to come up. Okay, and you can guess what it is going to be. The torsion is going to be only the change in the binormal. Alright, that sign will control everything, but you are going to forget the sign for the curvature. So this is what is going to happen in 3D. Okay, and so what you seem to be losing in forgetting the sign for the curvature is going to be gained by the sign of the torsion. That's what you have to understand ideologically. Okay, so we make the definition. So the definition is motivated by this: for a unit speed space curve gamma of s, okay, we define the principal normal. So it's called the principal normal. Okay, and the definition is similar to the signed normal. Okay, but with respect to this formula. So let me write it as n. So n hat of s will be 1 by ks t hat dot of s. Okay, so remember there is a dot on the t hat. Okay, so this is going to be the definition, and this definition is just reflection of it's motivated by the definition in the plane curve case. Again, let me repeat, in the plane curve case you have n hat subscript capital S, which is sine normal, and on the right side you have ks, which is a sine curvature. When you go to the space curve case, you forget the sign, you take only absolute curvature. Okay, ks is absolute curvature, it is always greater than or equal to 0. Alright, and because I am dividing by ks, I have to also put the condition that the curvature is not 0. So if curvature is not 0. So here is a very important thing. You write the principal normal only in the situation where the curvature is not 0. Okay, so this is already, the curvature not 0 is a very important thing, and you will see that eventually this is also going to come up, because you will not define the torsion unless the curvature is non-zero. This is like saying that you don't try to define for a plane curve, you don't define curvature where the velocity is 0. For a plane curve, you define curvature, first of all you have to assume that it is regular. That means the velocity has to be non-zero. Only then you define the curvature. And in fact, what is the formula for curvature? If gamma t is the representation, then it's norm gamma dot cross gamma double dot divided by norm gamma dot to the power of 3, and there is in the denominator you have a norm gamma dot that should not vanish. That's why you need regularity. You need the velocity to be non-zero to define curvature for a plane curve. And in the same way, when you go to space curve, we are actually going towards defining torsion, and the torsion you see is defined only when the curvature is not 0. Okay, so what you are saying is that you could have in the so you can ask this question that you could have done this for the plane curve, right? But then you should already have had this definition you should have one of the Frenet-Serret equations already as a definition. It will not be deduced, okay, but it has to be taken as a definition. You could do that, you could actually do that. But the point is, if you make a definition without any geometric intuition, it looks artificial. So the point is that you would like to come to a formula based on some geometric intuition. So that is the only thing. You could in principle use the same definition even for a plane curve. The only thing is that the way you define it, it will happen that the n cap you are defining will be the signed normal, and the k you will be defining will be the signed curvature. It will happen automatically, okay, all right. So it will happen, all right. The reason why it will happen is because you see this t cap, you see t cap is a unit tangent, its t cap dot is its derivative, so it's the acceleration vector, okay, and the acceleration vector has to point in the direction of the geometric normal towards the center of curvature. And what will happen is that your the sign of ks will be adjusted, the sign of k will be adjusted, so that the direction of n cap is correctly controlled, and essentially you will be if you want to keep k as always as positive, this n cap will change its direction, okay. So essentially you will be writing the same thing as this with this ks replaced by mod ks, and this n cap s being replaced by a minus sign whenever ks is mod ks is minus ks, which amounts to essentially using the sign curvature and sign normal. It will happen, okay. So now, so you have this principal normal, but watch, again important, just like to define, while defining the curvature of a plane curve, the velocity should not vanish. Similarly, when you are going to a space curve, we are only looking at a situation where the curvature doesn't vanish, all right. And the normal is defined like this, all right. Once the normal is defined, this is called the principal normal, okay. In the case of plane curve, it's called the sign normal. In this case, it's called the principal normal, okay. Now you can get the third vector, which is called the binormal, which is going to be a right-handed triad. So you see, so here is another definition. So the definition is, we define the binormal b cap of s to be, so it has to be a unit vector which is perpendicular to both t cap and n cap, okay, and so that t cap, n cap and this binormal, they form a right-handed triad that is given by therefore given by cross product. So this b hat s should be t hat s cross n hat s. So this is how you define the binormal, okay. So what is happening is that you have this kind of picture. So you have this, so this is your gamma of s, okay. So at every point you have this, you have one vector which is gamma dot of s, which is t cap of s, this is the unit tangent. Then you have you have the principal normal, this is n hat of s, okay, and then you have the third one, which is like this, which is b hat of s. So you have this, this is the frame, this is the orthonormal frame, a triad of three mutually perpendicular unit vectors, okay, and its right-handed is given because of this cross product, okay. They are just like your I, j and k unit vectors along x, y, z directions. The only thing with I, j, k is they are fixed, but here what is happening is that this is moving along with the curve, okay. So this is what is called the Frenet-Serret frame. So t cap s, n cap s, b cap s, this is what is called the Frenet-Serret frame. This is called the Frenet-Serret frame. Okay, and the Frenet-Serret differential equations will now be how to record how the derivatives of these three behave with respect behave with respect to these three, namely how they can be broken down in terms of these three. So what happens is that, you know, in the 2D plane curve case, what happened, you got this, you got t cap dot n cap dot is equal to 0 k minus k 0 t cap n cap, and I have to put an s, okay, and guess what is going to happen. So here in the 2D case, the coefficient matrix is skew symmetric matrix, and I mean it involves the curvature, okay. What is going to happen in the 3D case is that one more character is going to enter, and that's going to be torsion. So what will happen is, in the 3D case, 3D space curve case, what will happen is you have to now record the derivatives of the whole frame. So it is t cap, n cap, b cap, they are derivatives, dot, mind you dot is d by ds, okay. This will be, again, guess, you will get a skew symmetric now 3 by 3 matrix, okay. So you will get this part, you will get 0 k minus k 0, okay, and then what you will get is you will get a tau minus tau and 0 0 0, where this tau will now be the torsion, okay. So this is going to be the Frenet-Serret differential equation for the space curve case, okay. And again you get a skew symmetric matrix, and what are the two things that occur in the skew symmetric matrix? The curvature and the torsion. Mind you, the curvature is always non-negative, okay, or because you are not worried about the sign, okay, you are taking only the absolute curvature, okay, but the torsion will carry the sign, okay. And quickly to tell you what this torsion is going to be is, see, as you move along along a space curve, okay, there is going to be a, if you think of it as circular motion at every point, okay, instantaneously there is a circle about which it is turning, and then there is this centripetal force that is pointing towards the center of the circle. Now that is a curvature, okay, but what is happening is, you see, this circle itself is lying on the oscillating plane, and that plane is twisting. That is also happening. Now how the plane is twisting is recorded by how the normal to the plane is twisting, and the rate of change of that normal is exactly the torsion. So there are two twisting motions for a curve in space, okay. So here is the important thing that you should, you know, understand. There are two kind of twisting motions. One is instantaneously about the circle of curvature. The other is the plane which contains a circle of curvature, namely the oscillating plane, that itself is turning, okay. So that turning is also recorded, and that is the torsion, okay. So we have to see that, all right. So you see, so let me get back. So you see, you have, so this is what we are going to get. These are the, so this is what is going to be the Frenet-Serret for the, you know, 3D case, okay. So we have to understand what this torsion is, all right. Now so we have to now make some calculations. We have to define torsion, okay. We have not yet defined torsion, and then we need a formula for torsion, okay. And we also need to understand this that this torsion is change of an angle, the rate of change of an angle. Mind you, curvature is also rate of change of an angle. It is actually the rate of change of the you know, turning angle, if you want, all right. You want to do the same kind of thing for torsion. So so to begin with, let me make one you know, observation. We have defined this new you know, vector called the binormal, and somehow the way this binormal, you see, if it's pointing in the same direction, okay, it means that the oscillating plane is not changing, because the binormal is normal to the oscillating plane. If the binormal is fixed in the same direction, then the oscillating plane is not changing. That means essentially it should be a plane curve, all right. So if it's not a plane curve, it's a space curve, it will try to escape from the oscillating plane, okay, so that at the next nearby points the oscillating plane changes, okay, and that should be recorded by the change in the binormal, okay. So you need to understand how this binormal changes, okay. Here comes a very interesting thing. The instantaneous change in the binormal happens in the direction of the principal normal, okay. So that is the interesting thing, okay. So this is because of the math that is involved, all right, essential calculus. So let me explain this. So you see, so let me say fact, we would like to regard torsion as the rate of change of the binormal, okay, and the fact is the rate of change of the binormal is going to occur in a direction which is going to be in the normal direction or opposite to it, okay. This change is going to be in or opposite to the direction of the principal norm, okay. So you see the change in the binormal is going to be in the same direction or opposite direction, that is parallel to the principal normal. So that is, let me write this is the binormal b hat, its change is b hat dot, mind you dot is d by ds, this is going to be a scalar times n hat, okay, and guess what, this scalar is minus tau, where tau is the torsion, okay. Why is this minus sign put? Because of geometric considerations, okay. And why is this happening? This is because of mathematical considerations, okay. So we will justify this in the next lecture, okay.